Alright, welcome back. So today we are going to first have a quick recap of the first lecture. And this is where we stopped on Monday. So the memory cell area and the equivalent bit area. So here we use the F square to normalize different technologies to the same technology node. So the F can be like 20 nanometer or 30 nanometer. It's just a metric to normalize different technologies. So if you want to design SRAM, DRUN, design flash on a same technology node, then you want to use F to normalize that. So the unit area will be F squared. And then SRAM will be in this 150 to 300 F squared. DRUN is about 6 F squared. 2D NAND flash 4 F squared. This is for single level cell. That means one flash transistor store 1 bit. But as we see later, we will realize that flash can have higher density per bit. So per cell, you can have 2 bit per cell or 3 bit per cell. So equivalently, the bit area is the equivalent area that 1 bit of data occupy on the silicon footprint. So for the 3D NAND flash, so we have a number of the layers in the 3D stack. So if the number of layers is L, then equivalently on the 2D space, we will have this 4F squared divided by N. N is due to the N bit multi-level cell, and then divided by L, or is equivalent as this 4F squared divided by N times L. So here this is a bit area equivalent on the 2D plane. So for the 3D, if you think that you squeeze that into a 2D space, then this is the equivalent area for store 1 bit data on the silicon wafer. So any questions here? Yes? Latency? So here, as we discussed last lecture, for the 3D NAND, the density, of course, will increase, and the latency-wise will be roughly the same. Of course, depending on how many layers. If you have more layers, then the parasitic RC will increase, so you may suffer a little bit on the latency. Yeah, so this is due to the parasitic RC. If you have more layers, if you read the data from the bottom, then you need to pass along like a RC network from the bottom to the top. So the latency will suffer a little bit. All right, so then this is the area array efficiency. So this one is defined as area percentage occupied by the memory cell over the memory cell plus its peripheral circuitry. So for the DRAM or the NAND flash, the whole chip is about memory. So you have this memory cell array region, and then divided by the total chip area. So that is the array efficiency for the NAND or for the DRAM. But for the processor, like CPU, it's a little different, because on the CPU, you will have logic components. So there's no array efficiency for the whole CPU. You have to specify the array efficiency for certain blocks on the CPU. For example, here we can specify the array efficiency of the L3 cache on this CPU. So the total memory chip area will be this red box here for the L3 cache. And then you need to look into this box, how much is occupied by the memory. For example, here you may have those for the memories. And then you will count those as the memory cell area, and then divide by the total, that is the L3 block size. So this is the array efficiency for the L3 cache. Of course, if you want to look into the L2 cache array efficiency, you have to identify where the L2 cache is, and then you look into that and find out how much area occupied by the SRAM cell and how much area occupied by the peripheral circuits. So any questions here? All right, so then let's start our discussions today. So we will see a few examples, the real chip examples, to see where the memories are located on the chip. So this is an example from Intel. This is a 32 nanometer processor. And in this family, it has two kinds of design. The first one is a 6-core processor, which is shown on this graph. This is a photograph under the microscope. And then you can have another one, 2-core design. So for the 6-core design, you will have more than 1 billion transistors on chip. And in this case, this is enabled. So this region is L3 cache. And L3 cache is shared between cores. So from core 0 to core 2, those three will share the first L3 cache. And then the second group, core 3 to core 5, will share the other L3 cache. So in this case, we have in total 12 megabytes L3 cache. And here are the more details of the L3 cache. It's implemented by the 6-transistor SRAM cell, and each cell is about 0.171 micrometer square. And then it has two power supply. During the active mode, the power supply is 900 millivolts, and during the retention mode, that means you don't do the read or write, you just hold the data, then it's like 700 millivolts. And then here are more details about L2 cache. L2 cache will be within the core, so it's private. So each core will have its own L2 cache. The probably is somewhere here. It's not labeled. The probably is somewhere here. So the L2 cache, you see that it's still 6-transistor SRAM, but the SRAM cell size will be larger. In this case, will be 0.275 micrometer square. So the reason here is that as L2 cache, the transistor W over L is sized up to improve its speed. So here, this is basically the information about this processor. And here are more details about the total die size and the L3 cache size, and then the other specs of this processor. So this is what we see in the previous slide. So then the question here, let's calculate the array efficiency for the L3 cache in this example. So how do we do that? So you may have similar problems in your homework. So let's give you an image of the processor, then estimate the array efficiency of the L3 cache. So how do we do that? So let's take a look at this image. So here, first of all, you have the L3 cache region, like those two. And then you can use a ruler to estimate what is the area of the L3 cache region over the total chip area. You can use a ruler, and then you can get the X and Y, let's say X and Y dimensions for the L3 cache, and then you get the area, and then you divide by the total chip area. So if you do that, it's about 26% in this example, estimated by ruler. So those two regions over the total chip area, it's about 26%. So then array efficiency, as we defined earlier, will be the SRAM cell area within this block, within those two blocks. So the total SRAM area will be SRAM cell size, that is one SRAM cell size, multiply how many SRAMs in the L3 cache. That will be the total area occupied by the SRAM cell, and then divided by the L3 hash size. So this is the chip size for the L3 only, not the total chip, just the L3. So from the table before, we know that for the L3 cache, it's about 0.171 micrometer square. This is for one cell. And then from the information before, it says this is a 12 megabyte L3 cache. So you need to do a simple conversion, because here in this class, byte, 1 byte is 8 bits. So be careful about this big B and small b. So this is byte equals to 8 bits. So 12 megabyte is 96 megabits. So then in total, you will have 0.171 micrometer square times 96 meg. You can approximate that to 10 to the power 6 roughly, because mega is close to like 1 million. It's not exactly 1 million, because if you use 2 to the power, mega will be 2 to the power 6, then not to the power 6, I mean it will be 2 to the power 20, 2 to the power 20, then it's roughly like 10 to the power 6. So then you will get the total SRAM cell area, and then divided by the chip size for the L3 only. So L3 will be 26% of the total chip area, and total chip area is given by this information here, the die size, 240 millimeter square. So that will be 240 millimeter square. Of course, you need to convert the unit a little bit. Here is micrometer square. This is millimeter square. So you convert the units, and then if you do that, in total you will find out the L3 cache efficiency is only about like 27% in this example. So the efficiency is pretty low for the SRAM. So any questions in this example? Yes. This is from the information here, the total die size, that is for the whole chip, whole CPU chip. It's provided in the previous slide. Other question? That's a good question. I believe it's included the ECC bit. But for the SRAM, the ECC bit is not big portion, I would say. So the ECC should be included. Okay. All right. So then let's see if we have any questions online. Any people online? So for those attendees online, if you have questions, then you please post that into the chat box. I will check that once in a while. All right, so let's continue. So let's take a look at some other examples for the processor. So this is a PowerLine processor from IBM, and it was published in ISCC 2017. And ISCC is the top tier circuit conference, solid state circuit conference. So here, this is a 24-core processor implemented in 14-nanometer SOI FinFET technology. SOI is silicon on insulator. And this is made by GlobalFoundries. And this chip contains 8 billion transistors. So the total chip size is huge. This is like getting close to 700 millimeter square. So you can visually see that. I mean, it's like, yeah, you can visually see that this size. So, and it used 17 levels of the copper interconnect. That means the number of metal layers is 17, and the clock frequency is 4 gigahertz. So this is pretty high performance processor, because this was used to build the supercomputers by the DOE, the Department of Energy. There are two systems. One is called Summit, one is called Sarah. Those are basically assembled at Oak Ridge National Lab and the Lawrence Livermore National Lab. And those two are in the, I believe, in the top 3 or top 5 of the supercomputers in the world. So this Summit used to be the first, number 1, but I think last year Japan made a new one. So Summit probably number 2 these days. So anyway, so this is the power line processor, and let's take a look at what it includes. So 24 cores, okay. And then here you will see that we have 6 quad area, and each quad area will have 4 cores. So 4 times 6, in total you have 24 cores. And here you see that the L2 is shared between 2 cores, and L3 is also shared between those 4 cores. Then each core has its private 32 kilobyte L1 instruction cache and 32 kilobyte L1 data cache. So in the L1 cache, normally we will split that into 2 types. One is to store the instruction, like your command, from the ISA, the instruction set. And then the other one is your data. And then this L1 cache will be within the cores. But L2, in this case, is a 512 kilobyte L2 cache here. And then you have L3, those two L3 together will be 120 megabytes. So this is a huge L3. And in this example, the L3 is a little bit different than the regular processor, because here the L3 use EDRUN cell, not SRAM. So here L1 and L2 still SRAM, but the L3 will be EDRUN cell. EDRUN is embedded DRUN. So this is a unique feature by the IBM's design, because in IBM, historically, IBM is specialized with this EDRUN technology. So EDRUN has higher density than the SRAM, but the EDRUN will be a little bit slower than the SRAM. So here in this big chip, to hold more data, then IBM decided to use the EDRUN as L3 cache. So that's why you can have like 120 megabytes L3 cache. This is much larger than typical like 8 megabyte or 16 megabyte L3 cache in the other processors, for example, made by Intel or AMD. So this is the example from IBM. And the EDRUN, we will talk about that in more details later. So let's take a look at another example. This is AMD Zen 2 microarchitecture. So this is one of the most advanced processors today, and it was manufactured by TSMC 7nm FinFET process. So here, this was published in ISSA 2020, and in this processor, it has 4 cores, and each core will have its own private L1 cache and L2 cache. So L1 cache split into those 2 blocks, and those 2 blocks, one is for the data cache, the other one is for the instruction cache. And and then L2 is 512 kilobytes, and then L3 is 16 megabytes. This is shared between those cores. And in AMD's example here, all the caches are implemented by SRAM. So those are all SRAMs. But of course, the SRAM cell size will be different for different levels of the cache, because the transistor size W over L is to be fine-tuned for different levels of the cache. So here is some, I believe, is some zoom in of this AMD processor. So if you zoom in, then this is L3 cache region. So you see those regular patterns. Those are the, like those subarrays of the memories, and then in between you will have those like peripheral circuits. And this is zooming for the core and L1 cache region. So this is zooming for this part. And if you look at the core, then you will have this is L1 cache, instruction cache, and this is L1 data cache. And then you have other logic components like the ALU, the arithmetic logic unit. And then you have those like a CPU design, like a branch prediction, scheduler, and so on, and floating point computation. So those are the logic components. But overall, you can see that the logic component is pretty small in total. If you consider the whole chip, the logic is probably this part, and then all the rest are the memories. Here is a summary of this AMD Zen technology by TSMC. So here, this Zen 2 is the second generation. I believe they are working on Zen 3 these days with the 5nm process. But for this Zen 2, you see that those are the information. And here also it discloses some of the technology parameters. We will talk about that in more details later today. Like what is CPP, fin pitch, M1 pitch, and the number of metal track per standard cell library, and how many layers of the metal wires. So here in this case, it's 13 metals. So any questions here? Okay, so another example. So now this is a GPU. So this is from NVIDIA, 7nm A100 GPU. This is also one of the state of the art. And in this case, you see this is the image. And in the GPU, similarly, you have those like a cache hierarchy, L1, L2 cache. So here in total, in this GPU, you have around 87 megabytes SRAM. So here GPU has many cores. GPU, the number of cores is like hundreds, even thousands, because those cores are very small for the matrix operations. And here you see the L1 cache, and then instruction cache, data cache, and also the L2 in this case shared like 40 megabytes. And L1 in total is also about like 47 megabytes. This is because those 47 are splitted into like 100 SM, those cores. So each core is about like 192 kilobytes. So the overall architecture will be different. I mean, from the GPU versus the CPU, but still you will see those SRAMs widely used as a caches there. All right, then here let's switch the gear towards more standalone memory chips. So here is a DRUN chip by SK Hynix. This is a DDR5, and we will talk about the DDR protocol later when we talk about the DRUN. But this is one of the latest generations. So this DRAM chip in total has a capacity 16 gigabits, and it's in the Y1Y node. So here the companies, below 20 nanometer, they will not disclose the exact feature size for the DRAM and NAND flash. So they used to use like 1X, 1Y, 1Z node to represent the first generation, second generation, third generation in the sub 20 nanometer process. So here this data rate is 6.4 gigabit per second per pin. So this is the I/O data transfer rate from the DRAM chip. And then the I/O configuration, you can pass like 4-bit, 8-bit, or 16-bit at one time. So the total chip area is about 76 millimeter square, and the VDD is about 1.1, and then the high power supply to drive the wire line will be 1.8 volts. So here you see this is a very regular pattern in the DRAM chip, because in the DRAM chip most of the area are occupied by the DRAM cells. And here we have one bank group, and there are many banks in the DRAM. So we'll talk about the DRAM organization later. And then here is a NAND flash. And this is a 2D NAND flash. And we show the scaling of the 2D NAND flash. So here I believe this figure is proportional to the chip size. So in the 42 nanometer node, back in 2008, the total chip size is about like 900 millimeter square. And with the scaling, then the chip size gets reduced. I believe this is normalized to the like 128 gigabit equivalent chip capacity. I believe in the older generations, we don't have such huge chip. In those technology nodes, probably we have similar chip size, but the capacity will be lower, not 128 gigabits. In those cases, maybe like 32 or 64 gigabits. So this is normalized to the same capacity. If you normalize to the same capacity, then in the older technology node, you will have a huge chip, like close to 1,000 millimeter square, which is not realistic from the yield point of view, because you cannot build a large chip. If you build a large chip, if there's a defect on that chip, so the whole area is wasted. So you don't want to build a full large chip. So here it shows the scaling of the 2D NAND, and in 2015, that's probably the last generation of the 2D NAND, and the equivalent feature size is about 14 nanometer. So that is the last generation of the 2D NAND. And since 2015, then the industry switched to the 3D NAND, and we'll talk about that in more details later. So in the NAND array, so here you see that there are 4 planes. It calls planes. So each plane is like 32 gigabits. And then you have those row decoder and then column like sense amplifier and the control circuits. But most of the area occupied by those NAND cells. All right, so here is a quick summary of the first lecture. So memory is everywhere in the system, and actually you see most of the chip area occupied by the memory cells instead of logic. And then here the flash has been widely used today as SSD to fill the gap between the DRAM and the hard disk drive. And the increasing gap between the DRAM and flash offers opportunities for emerging memories, and we'll talk about that later. So here the array efficiency is a key metric to evaluate the chip design, memory chip design, because in the memory industry, cost is number one design consideration. It's the memory industry is very cost driven. So if you can find a way to lower down the cost per bit, then you will win the market. So the cost is number one. design consideration. All right, any questions for this lecture 1? Let me see if there's any questions online. No? Okay, I see one question. The NVIDIA A100 GPU, why they use turn L0, L1, L2 instead of L1, L2, L3 cache? Okay, so it's just a different way to indicate those 3 levels. So I think this is just used by the NVIDIA for their GPU. So there's no specific reason. But basically it represents the levels in the hierarchy. So you can think those are equivalent with the CPU design. Okay, let me break this